Welcome to the Deep Dive. We're here to unpack the technologies really shaping our world. So today, let's start with a scenario. Just picture this. You wake up, you step out of bed, and your place isn't perfectly tidy. Maybe there's a sock on the floor, a forgotten coffee mug, the usual morning clutter. Now imagine your household robot. It's not just blindly following some pre-programmed path it learned ages ago. Instead, it fluidly navigates around that mess. It anticipates where you're going to step next. It gracefully avoids, say, the water glass you left on the nightstand, a glass it's actually never seen before. It's not just executing commands. It feels like it truly understands its physical environment. So the question is, what kind of artificial intelligence would it take to make that happen? That seemingly simple, yet actually incredibly complex scenario. Today, we are diving deep into something that feels genuinely revolutionary. Foundational world models, or FWMs for short. This isn't just, another buzzword. It feels like a real paradigm shift in how AI perceives and interacts with the physical world around us.
We're going to unpack exactly what these models are, how they work, sort of under the hood. We'll look at the incredible breakthroughs happening right now in 2025. And importantly, we'll also tackle the significant challenges we absolutely need to navigate as these things become more integrated into our lives. So get ready. We're going beyond the headlines today to really help you grasp this pivotal shift in AI. Okay, so let's peel back the layers on this term. Foundational world models. The name itself, well, it gives us some clues, right? But to really appreciate the power here, we need to break it down into its two core components, foundation model and world model. Let's start with foundation models, or FMs. What are they? Think of an FM as a colossal general-purpose AI. It's very different from what we used to call narrow AI. Narrow AI is built for just one specific task, like maybe an AI that only predicts loan defaults. An FM, though, it's trained on truly immense, incredibly diverse data sets. We're talking billions, maybe trillions of words, millions of images, huge amounts of code, all scraped from the internet. And training these things requires just massive computational resources.
It's a huge undertaking. Yeah, the term foundation model itself,
Yeah.
it really gained traction after some Stanford researchers popularized it back in 2021. And it's pretty fascinating how quickly it's been adopted, isn't it?
It really is. You now see it explicitly mentioned in major global policy documents. Things like the U.S. Executive Order on AI, the EU AI Act, that swift inclusion in legal and strategic frameworks. It just underscores how much power and potential impact people perceive these models to have.
So what makes them so transformative? What are the key characteristics? Well, first, as I mentioned, it's just the sheer scale. Training data on a level that was, frankly, unimaginable just a few years back. Second, and this is really a game changer, they use a process called self-supervised learning.
Right, and that's crucial. It means they don't need humans to sit there and painstakingly label every single piece of data, which would be impossible at this scale. Instead, the model kind of generates its own learning signals. Like for a text model, it might predict a word that's been masked out in a sentence. It learns from the structure of the data itself. That's what makes training on internet-scale data actually feasible.
Exactly. And third, maybe the most revolutionary part, is their adaptability, this transfer learning capability. This is where the magic happens, really. An FM takes all that vast general knowledge from its initial training and then applies it to totally new, often very specific tasks with just a bit of extra training. We call that fine-tuning.
And that dramatically lowers the barrier to entry, doesn't it, for developing powerful AI applications. It makes cutting-edge AI much more accessible, more cost-effective to deploy across, well, countless industries.
And finally, FMs are increasingly multimodal. The early famous ones were mostly large language models, LLMs, focused on text. But the latest generation, they can seamlessly process and generate text, images, audio, even video. It's a much richer picture.
Okay, so that's the foundation model piece. Now let's tackle the world model part. The WM. At its core, a world model is basically an AI system that builds and maintains an internal, learned simulation of its environment. Think of it like the AI constructing kind of mental model of its surroundings. But it's not just static. It captures how things behave, how they change, and crucially, cause and effect.
So its main job is prediction.
Exactly. Its primary function is to predict future states, and importantly, the outcomes of potential actions it might take. Yann LeCun over at Meta, he describes it really well. He says the AI observes, and then it constantly predicts what might happen next. It considers its existing knowledge, sure, but also the potential effects of different actions, its own actions, or maybe actions by other agents in the environment.
So it allows the AI to imagine things, to run simulations internally.
Precisely. It can explore different sequences of actions inside its own model without needing to do costly or slow or maybe even dangerous trial and error out in the real world.
Okay, so the key features are, it's predictive. mapping current state and action to the next state.
Right. And it's action conditioned. That's critical. It explicitly includes the agent's own actions and its predictions. It has to reason about the consequences of its own behavior. And fundamentally, it has to be grounded in physics and causality. To make accurate predictions about the real world, it must learn an implicit understanding of physical principles, things like gravity, object permanence, cause and effect. Otherwise, its predictions would be useless.
So putting those two pieces together, foundation model plus world matter.
Exactly. That's where you get the foundational world model, the FWM. What's truly fascinating here is how these two powerful concepts converge. Essentially, an FWM is a foundation model, but one that's specifically designed and trained to serve as a world model. It takes that incredible scale, the general purpose pre-training, the adaptability we talked about from the FM paradigm, and directs all that power towards learning a predictive internal simulation of the physical world itself.
Can you give us a more formal definition then?
Sure. A foundational world model is a large-scale, multimodal AI system. It's pre-trained on vast datasets, primarily real-world interaction data, especially video. Its core purpose is to learn a general purpose, internal simulation of the world, one that can accurately predict future environmental states, and this is key, conditioned on actions. This powerful internal model then becomes the cognitive core for embodied agents. Think sophisticated robots, autonomous vehicles, navigating complex streets, that sort of thing.
So it's more than just combining ideas.
Oh, absolutely. It represents a fundamentally new architectural and philosophical approach. It's about using internet-scale data and self-supervised learning, the foundation part, to finally crack the long-standing AI challenge of physical grounding, which is what the world model concept has always been aiming for.
Are there concrete examples we can point to?
Definitely. We're seeing this synthesis clearly in leading projects. Google's Genie, for instance, they explicitly call it a foundation world model. And NVIDIA has their Cosmos World Foundation Model platform. The naming isn't accidental.
So the core idea is giving the AI an internal simulator, like an imagination.
That's a good way to think about it. An internal simulator, or maybe even better, an internal physics engine. Think about us humans. We constantly run mental simulations, right? You know if you drop a glass, it's going to shatter. You push a ball, it rolls. That's intuitive physics, a sophisticated internal world model. And FWM aims to give an AI agent something similar. It lets the agent run countless what-if scenarios entirely inside its own model, to dream or imagine possible futures resulting from its planned actions.
That feels like a huge leap from older AI models.
It's a monumental shift. Older models often just passively observed and classified static data, like identifying objects in a photo. FWMs, though, they actively simulate dynamic processes. That's the absolute key for enabling intelligent planning and reasoning in the physical world.
How does that compare to, say, a large language model?
Well, think about it. An LLM predicts the next word in a sentence. An FWM tries to predict the next state of the world. That's a task demanding a far deeper, more grounded understanding of reality.
That analogy of the AI's imagination is really powerful. But I think a lot of listeners are probably still thinking, okay, how is this really different from the LLMs we hear so much about? Where's the fundamental split?
That's a crucial question, absolutely. Because while LLMs are a type of foundation model, FWMs are tackling a very different kind of problem, especially for anything that needs to interact with the physical world, what we call embodied intelligence. The primary goal is different. An LLM, as you said, focuses on language, understanding it, generating it, conversation, summaries, creative text. An FWM, it's fundamentally built for simulating and predicting physical reality. And that core difference drives everything else.
Like the data they're trained on.
Exactly. LLMs ingest massive amounts of textbooks, articles, websites. FWMs consume a much richer diet. Video, sensor data from robots, logs of actions taken, real-world interaction data.
And their training objective reflects that too.
Precisely. An LLM predicts the next token, usually a word or part of a word. An FWM predicts the next state or the next frame of the world. And critically, it conditions that prediction on the agent's proposed action.
So the output is different too. LLM gives you text.
Right, text strings. An FWM generates simulated future states. That could be new video frames or maybe abstract vectors representing future possibilities.
Okay, so key strength of LLM is language fluency.
And synthesizing knowledge from text. Whereas an FWM's strength is its physical grounding, its ability to plan robustly in real-world situations.
Which points to their limitations too, right?
Yeah.
LLMs lack that grounding.
Fundamentally, they don't know what heavy means beyond how the word is used in text. FWMs address this, but they face huge computational costs, and that sim-to-real gap we need to talk more about.
That makes perfect sense. That grounding in physical reality, that's the core differentiator. An LLM can write a brilliant essay about gravity, maybe, but it doesn't intuitively understand gravity like a rock rolling downhill does.
Right. Exactly. FWMs are explicitly designed to build that intuition by learning the rules of the world from observation and interaction.
Now, another question people might have. How do FWMs stack up against other multimodal AI systems? We hear about AI that can process images and text, like OpenAI's CLP.
That's a good point. Many AI systems are multimodal. CLP is a great example. It learns rich connections between images and text descriptions. Excellent for image search, captioning. But FWMs are distinct in a deeper way than just handling multiple data types. What really sets them apart is their core function. They are predictive, action-conditioned dynamics models. Meaning they don't just associate data types like linking an image of a cat to the word cat. They learn to predict how the world evolves over time as a direct result of an agent's actions.
Can you give an example?
Sure. A standard multimodal model might look at a video clip and output a caption. A cat jumped over a fence. An FWM, given the same starting point, and maybe a proposed action like continue moving forward, would aim to generate the next video frames themselves, showing the cat actually landing gracefully on the other side.
Ah, okay, so it's that predictive simulative core that's the real difference.
Well, exactly. That's the fundamental architectural and functional differentiator that gives FWMs their unique power for interacting with the physical world.
And connecting this back to the bigger picture.
Right. If you connect this back, you see FWMs are directly tackling that profound, persistent problem in AI, the deep lack of physical common sense. This has plagued earlier architectures, especially LLMs. An LLM, for all its linguistic skill, can explain Newton's laws, but it has zero intuitive grasp of gravity. It doesn't know how stuff behaves in the real world. And that makes LLMs incredibly brittle, unreliable for anything requiring real physical interaction, controlling a robot, driving a car safely.
Yann LeCun has been quite vocal about this, hasn't he?
Extremely. He argues pretty forcefully that training AI only on text is basically a dead end if you're aiming for human-level intelligence. He often points out, a 4-year-old child processes vastly more information visually than even the biggest LLMs process through text. And doing that, the child builds this incredibly rich, intuitive world model about common sense about physics, how things work. He even jokes that a house cat probably has more common sense for physical planning than current AI.
So FWMs are the attempt to fix that.
They're the most direct and ambitious attempt. By forcing these large models to learn the world's rules through the really hard task of predicting future video frames, researchers are trying to instill that physical intuition, that common sense that AI has always lacked. It's about building AI that doesn't just read about the world, but actually understands how it works, how it moves, how it responds to actions.
That's a really clear distinction. So, okay, we've imagined this smart robot navigating the messy living room. We get that FWMs provide its imagination, but how do you actually build that imagination into a machine? Let's pull back the curtain a bit. What's the engineering look like?
Well, generally these systems follow a pretty standard canonical structure, a kind of tripartite design that's proven really effective. It usually has 3 main modules, all interconnected.
Okay, what's the first one?
First, you have the perception module, sometimes called the encoder. This is basically the FWM's senses its interface with the world. Its job is to take all that raw, high-dimensional sensory input, millions of pixels from a camera, complex audio waveforms, and compress it. It transforms that raw data into a much lower dimensional abstract representation. And this happens in what are called the latent space.
Why compress it? What's the goal there?
Efficiency and relevance. Mainly. You want to strip away irrelevant details, the exact texture of a wall, the precise lighting conditions, and capture only the essential semantic information, like the position and velocity of a ball, or the core meaning of a command. It's like getting a concise summary of a huge amount of data.
Makes sense. What's the second module?
That's the world model proper, also called the dynamics model or predictor. This is the real cognitive core, and it operates entirely within that efficient, low-dimensional latent space created by the perception module, its main job, to learn the dynamics, to act as a simulator, predicting how the world's state evolves over time.
So it takes the current state,
The current latent state, yes.
Yeah.
And a proposed action. And its output is a prediction of the next latent state. Often, this module uses recurrent networks, so it has memory. That's crucial for modeling complex stuff happening over time, like tracking an object or understanding a long sequence of events.
Okay, perception world model. What's the third part?
That's the agent or controller. Sometimes it includes a decoder, too. This module uses the world model to actually make decisions and achieve goals. It usually does two things. First, as a planner or actor, it uses that dynamics model to imagine the outcomes of different action sequences. It can simulate thousands of possibilities very quickly in that latent space to pick the path it predicts will lead to the goal or maximize some future reward. It's like mentally rehearsing strategies.
And the second thing, the decoder.
Right. Often there's a decoder that can translate those abstract latent states back into something humans can understand, like generating a video frame. This is super useful for developers because they can literally visualize the model's imagination, see what it's predicting.
And doing all this in the latent space is key for speed.
Absolutely critical. Trying to predict the future pixel by pixel. Incredibly complex, computationally nightmarish. By working with these much smaller, abstract, latent vectors, the FWM can run thousands, maybe millions, of simulations in parallel. That enables the massive imagination needed for effective planning and learning. That latent space isn't just a trick, it's the AI's cognitive sandbox, where it plays out possibilities way faster than real time.
That's a great breakdown of the architecture. Now, going back to how this imagination is built, what kind of actual neural networks are running these modules?
Good question. The specific network choices are really tied to what each module needs to do and the kind of data it handles. So for the perception module, the encoder, the part compressing sensory input into the latent space, you often see things like variational autoencoders, VAEs. They're designed specifically for learning these compressed representations. You also see advanced vision transformers, VITs, and convolutional neural networks, CNNs. These are really good at pulling meaningful features out of high-dimensional visual data like images and video.
Any examples?
Sure. The original pioneering world models work used a VAE. More recently, platforms like NVIDIA's Cosmos use a powerful pre-trained vision transformer called DOV2 as their observation model. Think of these networks as the AI's advanced eyes and ears, distilling sensory input.
Okay, what about the world model itself? The part doing the predicting in latent space?
For the dynamics model, yeah. Historically, recurrent neural networks, especially architectures like recurrent state space models or RSSMs, have been very effective. They're good at processing sequences and maintaining memory over time. The really successful Dreamer series of models, for instance, relies heavily on an RSSM for its core world model. Shows they're still powerful.
But transformers are everywhere now, right?
They are indeed. Transformers are increasingly used here too, mainly because they scale so well and can capture really long-range dependencies in time. You can use them as dynamics models, essentially predicting the next latent state token by token, kind of like how an LLM predicts the next word.
And for generating really realistic predictions, like future video.
For that, state-of-the-art generative models like diffusion models are becoming the go-to. They can produce incredibly high-fidelity outputs. Google's Genie too. The one that generates playable worlds. It uses a latent diffusion model to make its imagined futures look convincing.
Got it. And finally, the agent, the part that decides what to do.
For the agent or controller, common choices are things like multi-layer perceptrons, MLPs, or actor-critic networks. These networks learn a policy, basically, a strategy that maps states, observed or imagined, to the best actions. They optimize this policy based on the future rewards predicted by the world model. So the Dreamer agent, for example, uses an actor-critic algorithm trained entirely on those internally imagined trajectories. It learns good behavior without risky real-world trials.
Okay, architecture makes sense. Now, what about the data? You said video is key?
Absolutely essential. Data is the fuel for these reality simulations, and the capabilities of any FWM are directly tied to the volume and, crucially, the quality of its training data. Since the goal is predicting the physical world, it needs a specific data diet. And yes, large-scale video is paramount. Video is just incredibly rich. It inherently shows physics in action, object interactions, causality, how things change over time. That's why these big projects use millions of hours of internet video, YouTube, dash cams, everything.
But it also needs action data, right? To be action conditioned.
Yes, exactly. The model needs data that pairs sensory observations with the specific actions taken at that moment. For robotics, this often comes from human teleoperation, someone driving a robot remotely, and the AI watches the video feed and the control inputs, or logs from other robots.
And simulation data plays a role too.
A a huge role. High-fidelity physics simulators like NVIDIA Omniverse are heavily used. They let you generate almost infinite data, especially for rare or dangerous situations. Think a car skidding on ice or a robot handling something very fragile. Plus, synthetic data gives you perfect ground truth labels for everything, which is incredibly helpful for training.
So it's a mix.
Yeah.
Real internet video and simulation.
The most advanced projects use a hybrid strategy. They combine that precious, high-quality but scarce real-world interaction data with massive amounts of unlabeled internet video and scalable, perfectly labeled synthetic data. NVIDIA's Project Genie, for instance, explicitly combines all three. They reported something like a 40% performance boost compared to just using real-world data alone. It's about leveraging the strengths of each type.
So if I'm getting this right, we're basically giving AI the power to dream future realities and practice inside those dreams before acting in the real world. That's still kind of mind-bending. But how does that translate into the learning process? How does it absorb all that data, video, actions, simulations, and actually build that internal simulator?
It primarily learns through self-supervised learning. Remember, the training signal comes from the data itself, not human labels. The whole setup, architecture, data, objective is engineered to force the model to learn this deep, predictive understanding.
And the main objective is prediction.
Fundamentally, yes, prediction. The model is constantly trying to predict a future state based on past observations and actions. Its internal parameters, its weights, get adjusted again and again to minimize the error between its prediction and what actually happens next.
What forms does that prediction take?
The most intuitive is probably next frame prediction. You feed the model some video frames and the actions taken, and you ask it to generate the very next frame. By trying to get that generated frame as close as possible to the real next frame, pixel by pixel, the model is forced to learn everything necessary: object appearance, movement, physics like gravity, collisions.
Are there other ways?
Another powerful one is masked prediction. You hide parts of the input sequence, mask them out, and the model has to fill in the blanks. Meta's V-JEPA architecture uses a clever version of this. It learns to predict the abstract representation of a future video clip from the representation of a past one.
So it's not just about pixels.
Exactly. It pushes the model to learn deeper, more abstract concepts about how the world works, not just surface details, more robust learning.
And this training happens in stages.
Often, yes. You might first train the perception model, like a VAE, to get good at compressing video into the latent space. Then you train the dynamics model, maybe a transformer, on those latent tokens to learn the prediction rules within that compressed space.
Okay, let's zoom in on a few core technical ideas here, just to make sure we've got them. First, latent space. We've mentioned it a lot.
Right. Think of it as that compressed, abstract, internal language the model uses. Imagine trying to describe a complex football game with just a few key numbers: score, possession, time left, maybe momentum. That concise summary, holding the critical info. That's kind of like the latent space. A well-trained model learns a latent space where similar concepts end up close together. This allows for generalization and makes computation way more efficient. It's the AI's cognitive sandbox for fast imagination.
Got it. Second concept, representation learning.
This is really about how the AI learns these useful latent spaces or representations directly from raw data. The self-supervised training we talked about. It's designed specifically so the learned representations capture the dynamics, the causal structure of the world. That's what makes them so good for planning and decision-making later on. It's how the AI figures out the underlying logic of reality.
Okay. And third, that challenge you mentioned, sim-to-real transfer.
Yes, this is a major persistent headache in robotics and embodied AI. A policy, a behavior that works perfectly in simulation, whether it's a classic simulator or even a learned world model like an FWM, often fails, sometimes badly, when you try it on a real physical robot.
Why is that? The reality gap.
Exactly, the reality gap. Subtle but critical differences. Sensor noise is different in the real world. Friction isn't quite the same. Lighting changes constantly. Material properties aren't perfectly known. The simulation is always an approximation.
It's like training a race driver only on a perfect simulator.
And then throwing them onto a real track with bumps and wind, they'll struggle. Bridging this gap is a huge research focus.
How do they try to fix it?
Key strategies include domain randomization, basically making the simulation incredibly varied and messy, adding noise, changing parameters randomly. This forces the model to learn a robust policy that isn't brittle, that doesn't rely on the simulation being perfect. And the other key technique is fine-tuning. You take the model trained in simulation and then train it a bit more on a small amount of real-world data from the actual robot and environment. This helps it adapt to the specific nuances of reality.
So you could imagine the model dreaming all these future video sequences internally, preparing for a huge range of real-world possibilities, making the reality gap smaller.
That's the idea. The better the internal simulation, the more scenarios it can practice, the more robust it should become when facing the real world.
Okay, with that technical foundation laid, let's shift gears. Let's talk about the absolute cutting edge. What are the latest breakthroughs happening right now in 2025? What surprising applications are emerging?
Well, one that's generated a lot of excitement recently is Meta's V-JEPA 2. It's particularly interesting because its focus is squarely on learning physical reasoning directly from massive amounts of unlabeled video. It's really trying to mimic how humans learn just by watching the world.
And what's the key innovation there? Predicting abstract representations, you said.
Exactly. Instead of just predicting raw pixels, which can be messy and computationally heavy, V-JEPA 2 predicts these abstract representations of future video clips based on past ones. This forces it to learn deeper conceptual understandings of physics and object interactions, the underlying grammar of the physical world, not just memorizing visual details.
What's the impact of that in the real world?
It's pretty profound. They have a version, V-JEPA 2AC, which they fine-tuned on just a small amount of robot-specific data, and it can perform zero-shot planning and manipulation with a real robot arm.
Zero-shot meaning?
Meaning it can successfully pick up and place objects it has literally never seen before in environments it hasn't been explicitly trained in. It directly connects its learned visual understanding to precise physical actions. That's a huge step towards robots that can actually adapt to new situations on the fly.
That sounds incredibly impressive. But playing devil's advocate for a second, what are its limitations? Where does something like V-JEPA 2 still struggle?
That's a fair point. No model is perfect, right? While V-JEPA 2 is groundbreaking in learning abstract physical concepts, it still faces challenges common to many FWMs. For instance, maintaining perfect physical consistency over really long time horizons. That's still tricky. If you ask it to simulate a complex, multi-step task for, say, several minutes, errors can creep in and accumulate. Objects might start doing slightly weird things, maybe not quite obeying physics perfectly after a while.
Because it's learning from noisy real video.
Partly, yes, and the real world is just incredibly complex. So while it's fantastic for generalizing to new objects and figuring out immediate actions, really robust, long-term planning in highly dynamic, uncertain environments, that's still an active research area for all FWMs. It's a very powerful stepping stone, but definitely not the final word yet.
Makes sense. Who else is making big moves in this space?
Well, you really have to talk about NVIDIA. They're playing such a central strategic role in this whole ecosystem. They provide not just the crucial hardware the GPUs needed to train these monsters, but also these end-to-end platforms that are critical for FWM development.
Like their Cosmos platform.
Exactly. Their Cosmos World Foundation model platform. They describe it as an open, customizable platform specifically for physical AI. And they're showing how these FWM principles can apply beyond just robots. Look at their Earth-2 climate model. That's essentially a domain-specific FWM, a learned simulator for incredibly complex systems like global weather and climate forecasting. It shows the breadth of this approach.
And Project GO00, that sounds important for robotics.
Hugely important. Project GR00T, that stands for Generalist Robot 000 Technology. It's basically designed as a foundation model, a general-purpose brain for humanoid robots. It takes multimodal commands, natural language, maybe an image showing what you want done, and translates that into fluid, complex actions for the robot.
How does it work architecturally?
It cleverly combines a vision language model, VLM, for the high-level reasoning part, understanding the command, with a diffusion transformer that generates the smooth, continuous movements for all the robot's joints. It's designed as a base model that different robotics companies can take and adapt, fine-tune for their specific humanoid hardware.
So it's part of a bigger picture for NVIDIA.
Definitely. It plugs into a whole vertical ecosystem. They have the Jetson Thor computer for actually running the AI on the robot. And they have the Cosmos platform for generating the massive amounts of synthetic data needed to train models like GR00T in the first place. This kind of integrated approach is really what's accelerating progress in humanoid robotics right now.
So we've seen these technical leaps in specific platforms, but let's zoom out again. What does this mean for broader industries? The impact seems like it could go far beyond just the research labs.
Oh, absolutely. Foundational world models are poised to redefine several key areas. The most obvious one is humanoid robotics and embodied AI. FWMs are becoming that centralized brain for these general-purpose robots. This is what lets a humanoid understand a high-level command like tidy the room. Its internal world model allows it to then plan the whole sequence of complex physical actions needed: locate the cup, figure out a collision-free path, grasp it carefully, carry it to the sink, place it down gently.
And it can do this even if the room is messy or it hasn't seen that specific cup before.
That's the key. Robustness in cluttered, dynamic human environments and the ability to generalize to unfamiliar objects and situations. We're already seeing really impressive demos like 1X's Neo robot doing household chores or covariance robots handling complex sorting in warehouses. It's a shift from rigid automation to adaptable, intelligent help.
Okay, robotics is clear. What about autonomous vehicles?
FWMs are becoming absolutely critical there, too, for the next generation of safer, more reliable self-driving systems. Their main role is as a powerful predictive engine. An FWM lets the AV simulate the likely future actions of everyone else on the road, pedestrians, cyclists, other cars, literally fractions of a second into the future, and then plan its own actions accordingly.
So it's moving beyond just reacting.
Exactly. It's moving from simple reactive control, that car braked, so I'll slow down, to proactive, longer-term planning. Like, that car might merge in 10 seconds. Maybe I should subtly adjust speed now to make space and keep traffic flowing smoothly. Much more sophisticated, human-like driving.
And they help with training data, too.
Hugely. FWMs are used to create these data factories that generate massive amounts of synthetic training data for those really rare but critical edge cases. Things that are almost impossible to capture enough examples of in the real world: a tire blowing out on a wet curve, a deer jumping out from behind a truck. This allows for incredibly rigorous testing and validation in simulation in ways that would be impractical or just too dangerous to do on real roads. Companies like Wawabi with their Copilot 4D model, or WAVE, are really building their whole approach around this world model philosophy.
What about outside of robotics and vehicles?
Yeah.
Scientific discovery.
Yes, immense potential there, too. FWMs can act as incredibly fast, learned simulators for complex physical systems. Imagine, instead of running traditional simulations on supercomputers that might take days or weeks, a trained FWM could predict the outcome of an experiment, or model a complex process like protein folding almost instantly.
A GPT-3 moment for physics, you mentioned.
Some researchers are calling it that, yeah. The idea is you could specify desired properties, and the FWM could rapidly search through a vast design space to find, say, a new material with those properties, or optimize an experimental setup, accelerating discovery by orders of magnitude.
Are there examples already?
Early examples are emerging. Microsoft has their Aurora model for weather and climate forecasting, which is showing impressive speed and accuracy. They also have MatterGen for discovering new stable materials. And DARPA, the U.S. Defense Research Agency, even has a program called FoundSci, aiming to create an autonomous scientist AI, powered by these kinds of world models.
Wow. Okay, one more area. Gaming and content creation. How do FWMs fit in there?
This could be profoundly disruptive for entertainment. FWMs shift content creation away from being purely manual and labor-intensive towards being much more generative. And they go beyond just generating static assets like images or text. They can generate entire interactive, dynamic virtual worlds from simple prompts.
Like Google's Genie 2.
Exactly. Genie 2 is an 11 billion parameter FWM. You give it a rough sketch or a short text description, and it can generate a fully playable 2D or 3D world with consistent physics and a character you can control. And it learns how to do this just by analyzing huge amounts of unlabeled internet videos of people playing existing games.
The possibilities seem endless there.
Right. Imagine a child drawing a picture and having it instantly turn into a playable game, or a filmmaker live directing AI characters in a complex simulated scene just by giving them instructions, or generating infinite novel training environments for other AIs to learn in. It really opens up creative expression.
So connecting all these applications back to the bigger picture.
Yeah.
You mentioned a growing consensus about humanoid robots arriving soon.
Yeah, it's becoming increasingly clear. There's a strong growing consensus among many leading experts that genuinely capable humanoid robots could realistically arrive before 2027, largely driven by these FWM breakthroughs. Some even predict humanoids could be shipping in the millions before the end of this decade.
And this progress is fueled by that simulation flywheel idea.
Exactly. That simulation flywheel is key. FWMs enable much better, faster simulation. Those simulations generate higher quality synthetic data, especially for those rare critical edge cases. That data trains better, more accurate FWMs, which then enable even better simulations.
It's a self-reinforcing loop.
Precisely. Simulate, generate data, retrain, improve simulation. It's an incredibly powerful engine driving progress, accelerating disruption across all these areas: robotics, AVs, science, gaming. It really blurs the lines between the digital and physical worlds, doesn't it? These models learn from physical reality through video, use that to create better digital simulations, which then train agents to act more intelligently back in the physical world.
Can you visualize how that flywheel could fundamentally change how products are designed, tested, deployed across almost every industry?
It's potentially transformative. Think about designing a new car or planning a complex logistics network. This continuous cycle of simulation, data generation, and model improvement could compress development timelines dramatically.
That flywheel sounds incredibly powerful, almost inevitable. Are there any hidden friction points or significant bottlenecks in that process that maybe aren't immediately obvious?
Oh, absolutely. It's a compelling vision, that flywheel, but it's definitely not frictionless. One major point of friction is still that persistent reality gap we talked about. Even with sophisticated synthetic data and domain randomization, getting a policy trained in simulation to work reliably on a physical robot, it's still a serious engineering challenge. The real world is just noisy and unpredictable in ways that are incredibly hard to capture perfectly.
So the simulation is never quite perfect.
Exactly. And another bottleneck can be the quality of the synthetic data itself. If your simulator isn't realistic enough, or if the scenarios you simulate don't match the distribution of things that happen in the real world very well, then the flywheel might spin inefficiently. It could even teach the model the wrong things.
And the computational cost is still a factor.
A massive factor. Just running these ultra-high-fidelity simulations needed for good synthetic data, let alone training the gigantic FWMs on that data, requires enormous computing power. That remains a significant barrier. So, yes, the idea of the flywheel is powerful, but making it spin smoothly and effectively for every possible real-world application, that's still a huge undertaking.
Okay, let's unpack this from another angle then. The potential is obviously immense. We've covered that. But the path to widespread responsible deployment, well, it seems fraught with some pretty significant hurdles. Let's talk about the challenges, starting with the technical ones. First, you mentioned the immense computational cost and energy consumption.
It's staggering, really. Training a state-of-the-art FWM requires massive data centers, thousands of top-tier GPUs, running continuously for weeks, maybe months. The cost for a single training run can easily hit hundreds of millions of dollars. This creates a huge barrier to entry. It effectively concentrates the power to build these most advanced models in the hands of just a few very well-funded tech giants and government labs. It's not something a small startup can easily do.
Right. Second technical challenge: physical consistency and long-term coherence. You touched on this earlier.
Yeah, it's a persistent issue. FWMs can generate really impressive, realistic short-term predictions, like a ball bouncing convincingly. But maintaining that physical consistency, that logical coherence over longer simulations, that's still really hard. Over longer periods, you might see objects slowly distort, change color weirdly, maybe disappear when they go behind something and then reappear incorrectly, or even just violate basic physics, like that example of a dropped plate hovering instead of shattering. Making these generated worlds stable and physically plausible for more than a few seconds or minutes is a major research problem.
Okay. Third, modeling uncertainty and randomness. The real world isn't deterministic.
Exactly. It's inherently stochastic. Throw a ball, it won't land in the exact same spot every time. There's always variation. So a good FWM can't just predict one single future. It needs to represent and predict a whole distribution of plausible futures. Designing models that can accurately capture this uncertainty, predicting not just what might happen, but how likely different outcomes are, and do it efficiently, that's really complex.
And fourth, back to the big one for robots: bridging the sim-to-real gap.
Still arguably the most fundamental problem for any FWM intended for embodied AI. That policy trained in the simulator, even a very good learned world model, often just breaks when you put it on a real robot. That reality gap, the subtle differences in sensors, friction, lighting, materials, it trips up models trained only in the clean simulation. Closing this gap needs those techniques like domain randomization and real-world fine-tuning, but it's still a very active, very difficult area of research.
And these technical challenges, they lead directly into some pretty serious ethical and societal considerations, don't they? Especially because these FWMs are powering agents that act physically in our world. The stakes feel much higher.
Exponentially higher, absolutely. First, you have the classic AI alignment problem. How do we ensure the AI's goals and behaviors truly align with human values and intentions, especially when it's acting autonomously in the physical world? For an FWM controlling a robot, this is critical. Imagine giving it a simple goal like clean the kitchen. Without a deep, nuanced understanding of human concepts like care or value or don't break grandma's china, it might find a ruthlessly efficient but totally destructive strategy. Maybe it decides shredding all the dishware is the fastest way to achieve a clean state according to its metrics. Instilling that nuanced, value-aligned common sense, it's a deeply unsolved problem.
Then there's data bias.
A huge concern. FWMs learn from their training data, and that data comes from the real world and the internet, which are full of human biases related to race, gender, socioeconomic status, culture. The model inevitably absorbs these biases, and that could lead to robots or AVs behaving in discriminatory or unfair ways. If the training video underrepresents certain groups in certain roles, the robot might learn to interact less effectively or even unfairly with people from those groups.
And transparency and explainability. These models are black boxes.
Immensely complex black boxes, billions of parameters. If an FWM-powered car has an accident or a robot causes harm, we need to understand why it made the decisions it did. For accountability, for liability, for fixing the problem. But tracing a specific action back through the trillions of calculations inside the model, it's almost impossible right now. This lack of explainability is a major barrier to trust and regulation, especially in safety-critical applications.
Beyond those, there's the straightforward potential for misuse.
Yes, the dual-use nature of this technology is stark. The core capability of an FWM, enabling an agent to plan and execute physical actions to achieve a goal, is precisely what's needed for advanced autonomous weapons systems. The same tech that lets a robot plan how to pick a lock could be repurposed to plan how to identify and engage a target. It's recognized as one of the most dangerous potential applications of frontier AI.
And misuse in terms of information, generating fake content.
Absolutely. FWMs can generate incredibly realistic interactive video. This could be weaponized to create highly convincing deepfakes, interactive propaganda, personalized scams at scale. Imagine fake news you can interact with. It could manipulate public opinion, sow chaos, make it incredibly hard to know what's real anymore.
And finally, the broader societal implications seem profound.
They really are. Think about privacy and autonomy. FWMs are powerful prediction engines. If deployed widely in surveillance or marketing, they raise huge privacy concerns. A world where governments or corporations can accurately predict your behavior based on simulated futures. That could fundamentally change our sense of free will, create new forms of control. Then there's job displacement. The automation FWMs enable across manufacturing, logistics, healthcare, entertainment. It will inevitably displace human workers from many current jobs. New jobs will emerge, sure, but managing that transition equitably, avoiding massive increases in inequality, that's a huge societal challenge, and related to the cost issue, the concentration of power. Because building these models takes such immense resources, the power resides with a few large companies and nations. They get to define the capabilities and the embedded values of the AIs that will shape our world. That concentration carries significant risks.
It really feels like the technical and ethical challenges are deeply intertwined here.
Yeah. They absolutely are. The technical difficulty of explainability directly worsens the ethical problem of alignment. The technical need for huge compute power leads straight to the societal risk of power concentration. You can't separate them. Addressing the risks requires a holistic approach, treating tech development and ethical governance as two sides of the same coin.
So bringing this all together, what does this mean for the road ahead? Let's recap. Foundational world models. They're this powerful convergence, giving AI an imagination to predict and plan in the physical world. They're tackling that core problem of physical common sense, driving breakthroughs in robotics, AV, science, even entertainment. But, as we just discussed, getting to responsible, safe deployment means seriously tackling these huge technical and ethical challenges.
Exactly. And looking forward, the research trajectory involves several key directions to push these capabilities even further, while hopefully addressing some challenges. First, scaling and efficiency. While bigger models and more data have driven progress, there's a huge push to make FWMs more efficient. That's vital for accessibility, but also for getting them onto smaller robots, edge devices. Research here looks at new architectures like Mamba and techniques like distillation compressing big models into smaller ones.
Second, going beyond short-term predictions.
Right. Hierarchical and long horizon modeling. Current FWMs predict coherently for maybe seconds, perhaps minutes. The goal is to extend that predictive horizon significantly, enabling planning over much longer timescales. This likely means moving to hierarchical models, as people like Jan LeCun envision. Models that predict and plan at multiple levels of abstraction, from make coffee down to activate robot joint 7, like how humans think.
Third, more senses.
Richer multimodality, yes. To interact with the world like humans do, agents need more than just vision and text. Future FWMs need to integrate audio, touch for texture, force feedback, and proprioception, the sense of the body's own position, crucial for dexterity.
And finally, better reasoning.
Explicit causal reasoning. Current FWMs learn causality implicitly through prediction. A key research goal is to develop models that learn more explicit, robust causal representations. This should allow stronger generalization to totally new situations by reasoning compositionally about cause and effect, not just relying on learned correlations.
Where do FWMs fit into the bigger quest for artificial general intelligence, AGI?
Well, within the mainstream AI research community, the consensus is pretty strong now. World models are seen as a critical, probably indispensable component for AGI. Pretty much any serious definition of AGI requires understanding the world, reasoning about it, acting purposefully in it. Those are exactly the capabilities FWMs aim to provide. They're viewed as the most promising way to give AI that physical common sense, that intuitive physics that current systems like LLMs lack.
So it's a shift in how AI learns.
It represents a fundamental shift, yes. From learning mostly by imitation, like LLMs processing text, to learning through continuous interactive experience with the world. The internal world model is what makes that kind of efficient experiential learning possible.
What's the ultimate long-term vision here?
The ultimate vision driving a lot of this research is to create an AI that learns kind of like a human infant. Think about it. Infants spend months just passively observing. Their brains naturally build this rich, predictive model of reality. They learn intuitive physics, things fall down, solid objects don't pass through each other. People have goals, all without explicit teaching, just by watching. The goal is for a future AGI to have a similar cognitive infancy, trained on vast sensory data using self-supervised prediction to build its own foundational world model. And from that deeply grounded predictive base, the idea is that higher-level cognitive abilities, planning, reasoning, language, maybe even creativity would emerge more naturally.
So the FWM isn't the whole story for AGI, but it's the foundation.
Exactly. In this vision, the FWM is the essential, non-negotiable foundation upon which you build everything else needed for general intelligence. It's the means to achieve intelligent action in the real world, which is the ultimate goal.
As foundational world models continue to advance, enabling AIs to truly imagine and act in our physical world, how do you think this newfound capability will reshape our daily lives? And what responsibility do we all share in guiding its development ethically? Thank you for diving deep with us.